All right, so lesson 4 is going to be on solving exponential and logarithmic equations, which is something that you guys are probably going to be more familiar with than everything else we've done so far, because you've done a lot of solving equations. It's just a different type of equation. So a lot of this is going to be stuff you've already done, which is good. Something to break up the new material. So solving an equation, you always start off, make a line down the equal sign to separate your equation into two parts. So what you want to think about when you're solving an exponential equation, okay, this right here is an exponential equation because you have a variable in the exponent. As you can see, the 2t up there in the exponent. So what you want to think about is first isolating the base. Okay, so your base is, whatever your exponent is on. So right here, our base is 3. So we need to first think about get that base and the exponent by itself. So we're going to try to isolate this right here, get that by itself first. So what we need to get rid of then are the -4 and the ×2. Okay, and you do it just like you normally do, an equation if it was 2 times x minus 4. First thing we would do would be add 4. So we get 15. And then we've got 2 times 3 to the 2t minus 5. So to get rid of the ×2, we would divide by 2. So now we have 3 raised to the 2t minus 5 equals 15 halves, or 7.5. Okay, so now we've got the base by itself, which is what we wanted to start off doing. Once we have that base by itself, now we need to cancel out the base in order to isolate or get the exponent by itself, so that we can solve for t. So we need to get rid of a base of 3. Well, what's the inverse of base 3? The inverse of base 3 is log base 3, right? We talked about how those are inverses of each other. So to get rid of the base 3, we need to do the log base 3 of both sides of the equation. So I'm going to say, all right, do the log base 3. And over here, I'm going to do the log base 3 of 7.5. So as we talked about, one of our properties says if you do the log base 3 of a base 3, those cancel, and it just leaves the exponent, 2t minus 5. And over here we've got the log base 3 of 7.5, which you can type it in the calculator and get the decimal version of it using the log base feature on the calculator. So log base 3 of 7.5 gives us, and we can just round this off to 1.834. I usually like to go to the thousandths when I'm doing logarithms. Then add 5. So that's 6.834 and divide by 2. And you get t to equal 3.417. All right, so now we've solved for t. If you plug that decimal back in to the equation for t, you should be able to simplify it out and see that it equals 11. All right, let's look at one other one, and I'll let you try one. So right here, again, we need to isolate the base. Our base is e, not 4e. 4 is not part of the base because 4 is not being raised to an exponent. So we need to get the e by itself. So I need to get rid of subtract 3 first. So I'm going to add 3. Gives me 5. And then I need to get rid of the times 4. So I'm going to divide by 4. That leaves e to the 2x. 5 divided by 4 is 1.25. Now we got to get rid of the base e. Well, what cancels a base e? Well, log base e. Log base e, remember, is natural log. So I can take the natural log of each side, and that will cancel the base e and leave 2x. So then on my calculator, I can just hit the natural log button of 1.25, and I get the decimal 0.223. I divide it by 2 to solve, and I get x equals 0.112 if I round it to the thousandths. All right. So go ahead and pause the video, see if you can do the next one by yourself. Let me know if you need help. All right, so as you can see right here, the value that we get for x is negative 5.723. You can see the mathematical process I went through there, each step. If you have questions on that, let me know, and I can come by and explain it for you and clarify if you needed to. Let's go ahead and go on to a different type of exponential equation. So still exponential, but this one is in the form of like a quadratic kind of. So you can think of this as really being e to the x squared minus 3 times e to the x plus 2 equals 0. Because if I raise x to the second, it makes it 2x, right? An exponent raised to an exponent, you multiply them, and it gives you the 2x. So when I look at it like this, e to the x is really like my x. I've got something squared minus 3 times that something plus 2. So it's almost like x squared minus 3x plus 2. It's kind of the way I'm going to treat it. Well, I would have to solve that equation by factoring, right? Because I've got something squared minus a constant times that something, that same something. So I'm going to factor that using my xbox method. Well, multiplies to be 2 and adds up to 3. Well, that's 2 and 1. So I'm going to, in parentheses, put a 2 and a 1. And in front of the parentheses, I'm going to put whatever that something is that was being squared. Right here, of course, normally I use x, right? Because x is what's being squared. Right here, it's e to the x that's being squared. So I'm going to write e to the x in the front of both of them. I'm going to put a minus sign, right, on both of the factors. So I'm not sure why I put a plus, but I'm going to put a minus 2 and a minus 1. All right, now I can solve by setting each of those equal to 0. I got x squared minus 2 equals 0. Not x squared, x to the x minus 2 equals 0, and x to the x minus 1 equals 0. I'm going to add 2 to get the base by itself. Same thing over here. Now to get rid of e, right, we do log base e. A log base e is a natural log. And that leaves x. Over here, same thing, natural log of e to the x. We'll cancel and just leave x. So I figure out what's the natural log of 2 and the natural log of 1. Those are going to be my two answers. Natural log of 1 is, of course, 0, because whatever you raise to the 0 will give you 1. And the natural log of 2 is 0.693. So there are our two answers. We could plug in either one of those, and it should make that equation true. All right, so let's see you guys try this right here. It's very similar, just using different terms. You still do it the same way, factor it like you would a quadratic. Give it a try, and then we'll go over it. All right, so on this one, something interesting happens at the end. Once we set each factor equal to 0 and solve, we get one answer, 1.609. But when we try to solve the other one, we're going to get an error on the calculator whenever we type in the natural log of -1. So when that happens, that means you just have that one answer. The other one is an answer that doesn't work because you can't take the logarithm of a negative number. There's nothing I can raise something to make it negative. If I raise it to a negative, it just makes it into a fraction, right? So I can't raise something, can't raise e to something to make it -1. So anytime you have a logarithm of a negative, you know that that's not going to give you an answer. So when I take the natural log of -1, I don't get an answer from that factor. All right. So let's look at now at solving logarithm equations. So we did exponential equations. Now these are going to be solving logarithm equations. So we're still going to do the same thing. We're going to try to isolate the logarithm now instead of isolating the base. So we can see right here, here's our logarithm, natural log of x. So we need to get that by itself. So I got to get rid of the times 2, and I'm adding 5. So first we subtract 5. That leaves 2 natural log of x, and then 4 minus 5 is -1. Now we got 2 times natural log, so we'll divide by 2, divide by 2. So that leaves the natural log of x equals -1/2. Now to get rid of a logarithm, okay, so on exponential equations, we wanted to get rid of the bases, so we did a log base. Well, now we're wanting to get rid of a log base, so we've got to create a base. Means we have to make these two parts of the equation both exponents and put in a base that is being raised to these exponents. So if natural log is a log base e, we can cancel a log base e with a base e. So we're going to write a base e raised to the natural log of x. Okay, so again, I'm raising each part of the equation. So I'm making those exponents and putting in the base that is necessary to cancel the logarithm that I've got in my equation. So e raised to the natural log will cancel and just leave x by itself. And then I've just got to type in e to the -1/2, and you can use the e button on your calculator to do that. And whenever you type those in, you should get 0.607. Alright, so x for that one's 0.607. Now let's do this other one. Okay, so this one, your logarithm, you got 2, one on each side of the equation. So each one of them is already isolated. You got log base 3 of 5x minus 1, and on the right you got log base 3 of x plus 7. So we need to cancel both of those log base 3's. To do that, we'll do a base 3. So we got 3 raised to the log base 3, 5x minus 1. And over here, we'll do 3 raised to the log base 3 of x plus 7. So the base 3 and log base 3's cancel. Just as 5x minus 1 equals x plus 7. Now it's a very simple equation, like algebra 1 type equation that you're used to doing. So we get x equals 2. Now on these also, right off the bat, you can tell that 5x minus 1's got to equal x plus 7 because both of them are having a log base 3 done to them. So if I do the log base 3 of one thing and it equals the same log base 3 of another thing, those two things got to be equal to each other. So we did it algebraically, but common sense tells us that 5x minus 1 has to equal x plus 7 if the log base 3 of each of them equal each other. So either way you want to do that's fine. Go ahead and try this one, pause it, and give it a try. Let me know if you need help. So right here you can see first we divide by 2, and then we've got our logarithm isolated. It's a log base 5, so we have to create a base 5 to cancel the log base 5. So I've got 5 raised to the log base 5 of 3x and 5 raised to the second. Those cancel on the left, just leaves the 3x, and I get 25 on the right. Divide 25 by 3, you get 25 over 3. So now, anytime you're solving the logarithm equation, it's important to realize that you can't do the logarithm of a negative number. So anytime you get something for x, for a logarithm equation, you really need to double check and plug it back in and make sure that that's an answer that actually works. Because if it's an answer that you plug in and it makes you take the logarithm of a negative, then it's what we call an extraneous solution, and you can't use it as an answer. Okay, so none of these do that in any of these problems so far, but you will get some that happens on. You know, if we plug 25 over 3 back in for x, well, 25 over 3 times 3 is 25, and we're going to be taking the logarithm of a positive number. But some of these you might get an answer where if you plug it back in, it's not going to work because it'll make you take the logarithm of a negative number. So you need to check for those. So that's what we're going to do on some of these right here. So this first one, notice this one, you've got 3 logarithms in this one equation. So what you've got to do in this situation is combine 2 logarithms into one, all right, to give yourself a way to cancel them out. Okay, so you can't do anything until you combine logarithms into one. So on the last lesson, we talked about expanding logarithms and condensing logarithms using the product property, the quotient property, and the power property. So we need to be able to use those properties here to combine or condense logarithms into one logarithm. So we see right here we've got the natural log of this plus the natural log of this. Since they're adding, we can use the product property and just combine those into the natural log of x minus 2 times 2x minus 3. So we're going to do one logarithm of those two things multiplied together. Our product property tells us that we can do that. All right, so now let's go ahead and multiply those out and FOIL them out and see what we get. It's going to be 2x squared minus 4x minus 3x is minus 7x, and then minus 2 times minus 3 is positive 6. So that simplifies into the natural log of 2x squared minus 7x plus 6. Over here we have 2 times the natural log of x. All right, so at this point, we can use the product property on the logarithm on the right side to move the 2 to be an exponent on the x, because we want just the natural log of something. So when we do that, I'm just going to go ahead and erase this one and just save myself from having to write the entire right side again. So make that natural log of x squared. So now we can get rid of our logarithms because we've got the natural log and a natural log by themselves. So we can say, all right, we'll just raise e to the natural log of 2x squared minus 7x plus 6, and e raised to the natural log of x squared. E raised to the natural logs cancel, such as 2x squared minus 7x plus 6. And on the right, we have x squared. There's an e and natural log cancel over there also. Okay, now it's just a quadratic equation. So we minus x squared, minus x squared. So we got 1x squared minus 7x plus 6 equals 0. Then we can solve that by factoring a quadratic. What multiplies to be 6 and adds it to be 7. 6 and 1. So we got x and 6, we got x and 1. And we're going to use a minus sign on both numbers. So minus 6, minus 1. Set each of them equal to 0. So we get x equals 1 and x equals 6. As of right now, those are both answers, but we need to check to see if we have any extraneous solutions. So we need to determine if we plug those in, 6 and 1, will we ever take the logarithm of a negative? So let's check. If I plug in 6 right here, will it make it negative? No, that's still a logarithm of a positive. What about 6 right here? 2 times 6 is 12 minus 3. Nope, that's positive. Plug in 6 right here. Nope, that's all right. So we can do the logarithm of 6, and that'll be fine. Now our other answer is 1. So 6 is good. Let's try 1. If we plug in 1, will we ever get the logarithm of a negative? Right here, 1 minus 2. That's going to be negative 1. So we're going to take the natural log of negative 1, which is not possible. So that means that 1 is actually an extraneous solution. Even though we got it as an answer and we solved, it's not really a real answer because it's not possible to plug it in and it show the equation to be true. So the only answer we have is x equals 6. I'm going to go ahead and pause it. You guys try this one and we'll go over it. Make sure you check for extraneous solutions. All right, so on this one, might be a little bit tricky because you have to do quotient rule. So the tricky step comes right here. Okay, so this might be something that's new for you because we had, before I did this step, we had x plus 5 equals x minus 1 over x plus 1. So what you've got to do is, to get rid of this fraction, multiply both sides by x plus 1. So that's what I did. I have times by x plus 1 on the right and times by x plus 1 on the left. And that will cancel out over here and leave just x minus 1 on the right. Down on the left, you have to FOIL, distribute. You get x squared plus 6x plus 5 equals x minus 1. So then in the next step, make everything equal 0. So I subtract x and add 1 to both sides. And I'm left with this quadratic equation, x squared plus 5x plus 6 equals 0. I factor that and solve each factor. I get x equals negative 2 and x equals negative 3. So now I've got to check for extraneous solutions. So I go and plug both of those back in, and I see that in this logarithm, using that one, both numbers, when I plug them in, make me take the logarithm of a negative, which is not possible. So neither one of those are actual answers. So that means that this problem has no real solution. Okay, no real solution on this one. All right, so now let's look at when we would actually use this in real problems, real life problems. So remember we talked about the compounding interest problems. So let's look at one like that. So you could use this in real life. You deposit $500 in an account that pays 6.75% interest, compounded continuously. How long will it take your money to double? All right, so continuously means we're going to use the PERT formula, right? So the amount is going to be P times E raised to the RT. The amount that we have is going to be A. Okay, well, how much do we want A to be right here? Well, we want it to double. So if we want it to double, we want to see how long will it take me to get $1,000? Because if I'm doubling 500, that gives me 1,000. P is the principal, the amount I start off with, 500, times E raised to the rate, which is 6.75, so 0.0675, because you got to make it a decimal. And then T is what I'm trying to find. I'm trying to solve for T. So now we can just solve this equation. It's an exponential equation. We've been practicing these, so we're going to get rid of everything but the base, isolate that base E. So I need to divide by 500. Divide by 500. 1,000 divided by 500 is 2. I've got E raised to 0.0675t. Now, how do we get rid of a base E? We do a log base E, or a natural log. So I do natural log of both sides. Over here that cancels, leaves 0.0675t. And then over here I've got the natural log of 2, which is 0.693. Now I divide by 0.0675. 0.0675, and I get T is going to equal 10.27 roughly. So about 10.27 years, or 10 years, 3 months roughly, if you want to think of it, how many months, because 0.27 is a little bit over a fourth of a year, which is 3 months. So it's going to be about 10 years, 3 months, somewhere around there to get my money to double. All right, so I'm going to go ahead and pause the video. You try this last problem, and I'll go over it. All right, so we just solved this equation right here. We added 2.983 and then divided by 15.206 so that we isolate our logarithm. Now, once we got the isolated logarithm, we need to solve it by raising that logarithm to the base. So the logarithm is log base E, so we need to use a base E. So right here we do a base E raised to 3.156 and a base E raised to the natural log of t. That cancels out the logarithm and just leaves t. And E raised to 3.156 is 23.465. Now, again, the question is, during which year did the average salary reach $45,000? Well, 23 is not a year, right? It's not the year 23, obviously. We got to remember that t equals 5 represents 1985. So if t is 23, that's 18 years later, right? If 5 was 1985, we're talking about t being 23, that's 18 years later. So 18 years after 1985 would be the year 2003. So 2003 is the year that the average teacher's salary reached $45,000. All right, let me know if you have any questions on this stuff. If you don't, you can go ahead and practice right here, and just let me know if you need any help.